Hi, welcome to my channel. In this video, I'm going to explain minimum cost spanning tree or minimum spanning tree, just introduction part. First, I'll give what is the definition of spanning tree. After that, I'll give what is minimum cost spanning tree. Just by taking some examples, I will show you how to construct a spanning tree and the minimum cost spanning tree for this. See, what is spanning tree? See, if you see the definition of spanning tree, it is a subset. Generally, we can construct spanning tree from the graph, given graph. Okay. So from the given graph, we are supposed to construct a spanning tree. So if you compare spanning tree with the graph, ultimately the spanning tree is a subgraph. Okay. So we can define spanning tree as a subset of an undirected graph. Subset means in terms of edges we say. Okay, subset of the given graph, all the vertices must be connected without leaving any edge, any vertex. We must connect all the vertices in the graph. We must consider all the vertices for constructing spanning tree, but it should be a tree, not graph. Okay, so if we take the graph as a z, then we construct a spanning tree. But that particular spanning tree should contain all the vertices. Generally, we represent a graph as z equal to v comma e, where v is number of vertices, e is number of edges. Okay, na? But in spanning tree, suppose if you represent spanning tree as s, that spanning tree should contain all the vertices without leaving any vertex in the graph. You must consider all the vertices in the graph in tree also, but without making any cycle. Okay, na? Spanning tree should not contain any cycle. So if you see the graph, the given graph Z, this Z has three vertices A, B, C. Now there are three edges A to B, B to C, C to A. There are three edges. Then the possible spanning trees are constructed below. Possible spanning trees. All the spanning trees are containing all the vertices of graph. See, first spanning tree A to B, B to C. Second spanning tree A to C and A to B. Third spanning tree A to C and C to B. These are the edges available are presented in spanning trees. But if you verify the vertices, the number of vertices which are connected in spanning tree are equal to the number of vertices in the graph. We cannot leave any vertex. You must consider, you must include all the vertices of a given graph in spanning tree and construct all the possible spanning trees. All the possible spanning trees. Just I will give one logic. Suppose if you remove A to C edge, then we get one spanning tree because the removal of that particular edge is removing the cycle. If we remove C to B edge, then C to B is also removing the cycle, but we are not removing C and B vertices in the tree. We are not removing C and B vertices, just we are removing edge from the graph. Also, if you remove AB edge, just the connected link between A to B, then we get another spanning tree. So like that we can construct even 4 nodes graph is there, or 5 nodes graph is there, or 6 nodes graph is there, whatever it may be the given graph. Our ultimate goal is including all the vertices of a graph in tree, and you must verify that whether that particular tree is containing any cycle. Just remove one by one edge and construct spanning tree. Just in the slides given, ABC triangle. The triangle is containing 3 spanning trees. I will tell you how many number of spanning trees are possible. For any given graph. There is an equation, very simple equation. Just by using that equation, we can say that these number of spanning trees are possible. That too, the complete graph. That too, we should have complete graph. This is completed because from each vertex to every other vertex, there is a connection. What do you mean by completed graph? The completed graph is a graph that contain the edges from all the nodes to all the other nodes. Suppose if you consider A is containing edges to CB, and C is containing edge to AB, B is containing edge to AC. Is it clear? Okay, now this is completely connected graph. This is completely connected graph. This completely connected graph has 3 spanning trees. I will tell you the very simple equation is there. Just by using this equation, we can calculate the number of spanning trees. Like that, any graph, even you take 4 edges graph, but the spanning tree is possible if the graph is undirected. Because from the directed graph, sometimes we cannot reach some nodes. Suppose if A to C and A to B direction is there, C to B is there. From A to C, A to B is the directed graph, and C to B is there. from this we cannot reach C. From this we cannot reach A, because from C we cannot reach, because from A to C is edge, from A to B is directed graph, directed. But A to C and B we reach, but C to A we cannot reach, B to A we cannot reach. Then there is no possible spanning tree for this. Okay, so if you want to construct a spanning tree, then that the graph must be undirected. Then only the spanning trees are possible. We can construct the required number of spanning trees by using this graph. Then suppose I have already told, if all the vertices are connected in the graph, then only the spanning trees are possible. There exist many spanning trees. I will tell you how many spanning trees. Below I have given in properties, I have given one equation. Just based on that equation, we can calculate how many number of spanning trees are possible. Is it clear? Suppose if the graph is completely connected, if graph is connected, disconnected means some nodes are out of this particular graph, then we cannot get spanning trees. If all the nodes are connected as a single unit, that too that graph is undirected, then there is a possibility of constructing spanning tree. So like that we can get more number of spanning trees from the graph. Okay, so then what are the properties of spanning tree? As I told earlier as definition, a spanning tree doesn't have any cycle, because you must include all the vertices. What do you mean by tree? Tree must not contain any cycle. If cycle is there, again it becomes graph. Okay, so spanning tree doesn't have any cycle. Whatever the edges that are making cycle, you are supposed to remove those edges in the graph. Like that, construct all the possible spanning trees. Okay, na? So another property is any vertex you consider, from that vertex we can reach any other vertex. I have already told. So if graph is completed, or if graph is given, so you select any vertex. From that you are supposed to reach all the remaining vertices. Then only the construction of spanning tree is possible. Otherwise, if any node is unreachable, then we cannot consider that node in the spanning tree. Then we say that there is no spanning tree possible. Okay, then I have already told you now how many possible spanning trees we can construct. Suppose if a graph is completely connected with n vertices, means what do you mean by completely connected? From each vertex there is a edge to all the remaining vertices. From each vertex to all the remaining vertices there is a direct edge. There is a direct edge. Then we say that that is a completely connected graph like this. From A there are two edges. One is to C, another is to B. From B we can reach A and C directly. From C we can reach A and B directly. Like this. Like this, if graph has from each vertex to all other vertices, if there is a direct edge, then we say that that is complete graph. For complete graph with n vertices, you can consider any number of vertices. Suppose if that vertex number is n, vertices number is n, then the total number of spanning trees possible is n power n minus 2. What is n? Number of vertices. N is the number of vertices. Then if you go back to this, how many number of vertices are there? 3 vertices. So 3 power 3 minus 2. What is 3 power 3 minus 2? 3 power 3 minus 2 is 1. So 3 power 1. There are 3 spanning trees possible. Suppose if we consider 4 vertices graph, if graph is completely connected means from A, suppose A, B, C, D are there. From A, we have to reach C, D, B, C, D directly. From B, if we have direct edges from B to A, C, D. Suppose from C, you have direct edges to A, B, D. From D also, if you have direct edges to A, B, C, D to A, B, C, then that is completely connected graph. Then that particular graph can have 4 power 4 minus 2. 4 power 4 minus 2 means 4 power 2, 16. So we can construct 16 possible spanning trees. 16 possible spanning trees. Here we get, in triangle, we get only 3 possible spanning trees, because number of nodes is the base and power is number of nodes minus 2. So 3 power 3 minus 2, that is 3 power 1. Only 3 possible spanning trees are there, because if you remove AC edge, we get 1 spanning tree. If you remove CB edge, we get another spanning tree. If you remove AB edge from the graph, we get another spanning tree. Then there are only 3 possible spanning trees for this particular graph. Is it clear? That is another property. And last property is a spanning tree constructed from n node graph. You can consider any number of nodes graph that contains exactly n minus 1 edges. See here. How many edges are there in spanning tree? How many nodes are there? 3 nodes are there. There are 3 nodes. Okay, A, B, C. Then every spanning tree must contain only two edges. Two edges are enough to connect three nodes. Suppose if we include one more node, then it makes cycle. Only one edge is left. Only one edge is left in spanning tree. If we connect that edge, suppose in first spanning tree, AC edge is absent. If we connect AC edge, then it makes cycle. In second spanning tree, BC edge is not present. If we connect BC edge, it makes cycle. In third spanning tree, AB edge is not present. That edge is there in graph. But if you consider that edge, it makes cycle. Okay. So then if number of vertices are n, then there are exactly n minus 1 edges required to construct a tree by considering all the vertices. So if two vertices, for connecting two vertices, one edge is enough. For connecting three vertices, two edges are enough. For connecting four vertices, three edges are enough. Like that, for connecting n vertices, n edges are enough. N minus 1 edges are enough. For connecting n edges, n vertices, n minus 1 edges are enough. That's what I told in this point. Okay. So for n node graph, exactly n minus 1 edges are required to construct a spanning tree. Okay. This is about the basic information of spanning tree. Okay. Then what is minimum cost spanning tree? Or we can also call it as minimum spanning tree. Minimum cost spanning tree or minimum spanning tree. So in earlier properties, what I told, number of spanning trees possible are n power n minus 2. So among n power n minus 2, suppose if graph is associated with edges, weights, here there is no weight. Suppose if you assign weights as, suppose A to B weight is 2, A to B to C weight is 4, and A to C weight is 6. So like that, if we assign weights, then for weighted graph, we can construct a minimum spanning tree or minimum cost spanning tree. Okay, na? So whatever the trees you construct, after constructing a tree, calculate the sum of all the edge costs. Calculate the sum of all the edge costs. I will tell you the one example later. Sum of all the edge costs. So whichever is minimum total, then which we select that particular tree as minimum cost spanning tree. Just what I am saying here. Okay. So the cost of the spanning tree is, how can we get cost of the spanning tree? The sum of costs of its edges. Okay, now whatever the edges you are considering for constructing spanning tree, just sum of all the edge costs associated with that particular edges, then we get cost. Then what is minimum spanning tree or minimum cost spanning tree? What is minimum cost spanning tree? Out of n power n minus 2 spanning trees, once after calculating each and every spanning tree cost, whichever is minimum, we select that particular spanning tree is minimum cost spanning tree or minimum spanning tree. That's what I told in definition. So minimum spanning tree is a spanning tree with the minimum cost than all the remaining possible spanning trees. All the remaining possible spanning tree means number of spanning trees possible are n power n minus 2. Is it clear? N power n minus 2 or number of possible spanning trees. So out of n power n minus 2, you must select one spanning tree with the lowest cost. Then the lowest cost spanning tree is treated as minimum cost spanning tree. So what is the spanning tree? Now you got idea. What is minimum cost spanning tree? Now you got an idea. Okay. So MST means minimum spanning tree is a connected, weighted, undirected graph. Is it clear now? So that connects all the vertices together. What I told, all the vertices we need to consider with the minimum edge cost, with minimum edge weights. Okay. You must have all the vertices of a graph for constructing spanning tree, but every time while we are including edges to spanning tree, that edge cost must be minimum among all the remaining edges. Like that, we need to select minimum cost edge every time. So if we construct all the edges with the edges with all the vertices of a graph, then we say that that is minimum cost spanning tree or minimum spanning tree. Every time we are applying criteria as minimum. Every time, whenever you select edge among all the remaining edges, the selected edge cost must be less than all the remaining edge costs. Like that, we need to select one by one edge from the graph and include that edge into spanning tree and construct spanning tree. But at most, we select n minus 1 edges, maximum we select n minus 1 edges for constructing n vertices spanning tree. Okay. So like that, we construct a minimum spanning tree. But here, there are two algorithms possible for constructing minimum spanning tree or minimum cost spanning tree. One is Prim's algorithm, another one is Driscoll's algorithm. I will explain these two algorithms in next video, but I will show you here So one example for constructing minimum spanning trees. But out of these spanning trees, which is minimum, we can easily say, okay, suppose if we take four nodes graph or four vertices graph, there are how many edges? There are 5 edges. This is not completed because T to A edges also must be there. Otherwise, we cannot treat it as complete connected graph. If C to A edge is also there, then from each edge there is a direct connection with all the remaining edges. If A to C is also present, then how many spanning trees are possible? I have already told. If graph is completely connected, what I told earlier, if graph is completely connected, if number of nodes are 4, then 4 power 4 minus 2 number of spanning trees are possible. So 4 power 4 minus 2 means how many? 16. So 4 power 2, 16 possible number of spanning trees we can construct from complete graph if A to C edge also there. Okay, na? So based on available graph, suppose if you construct some spanning trees, suppose one spanning tree is A to B, B to D, D to C. This is one spanning tree. Is there any cycle here? But we included all the vertices. So first prior or important point is you must include all the vertices of a given graph into spanning tree. Okay, so this is one spanning tree. A to B, B to D, D to C is one spanning tree. Here all the vertices are present. Number of vertices are 4. Then at most, it means maximum 3 edges are enough. 3 edges are enough to connect 4 vertices. Then A to B edge cost is 5. B to D edge cost is 2 and D to C edge cost is 4. Then how much? What is the total cost of spanning tree? 11. If you go to next tree, A to B, A to D, D to C edges are selected. Okay, but all the vertices are present. Please observe, all the vertices are present. Then 5 plus 5 plus 4, 14 is the spanning tree cost. In the next spanning tree, A to B edge is present, B to C edge is present, C to D edge is present. We cannot include other edges because if we include one more edge which makes cycle, even you include any edge, suppose if you include B to D edge, it makes cycle. A to D edge, which makes cycle. If all the vertices are present in the spanning tree and the number of spanning tree that are connected with the one less edge, then that particular tree is called spanning tree. We cannot include any other edge. If you include any edge, that inclusion makes a cycle. Okay. So here third spanning tree, cost of third spanning tree is 10 because A to B cost is 5 in the graph. B to C cost is 1 in the graph and C to D cost is 4 in the graph. If you include B to D, though that particular tree cost, edge cost is 2, which makes cycle. Okay, but this particular spanning tree cost is 10. All these are possible spanning trees we can construct. And the last spanning tree, if you observe, A to D, D to B, B to C, these are the edges included. If you include A to B, which makes cycle, if you include D to C, which makes cycle, that's why we omitted the edges which are making cycles in the spanning tree. Is it clear now? Then what is the cost of this fourth spanning tree? A to D cost is 5 plus D to B cost is 2 plus B to C cost is 1. Is it clear? Then this particular spanning tree cost is 8. Then which is minimum cost spanning tree now? Out of these 4, minimum cost spanning tree is fourth one. If we compare all the spanning trees cost, fourth spanning tree cost is 8. All the remaining spanning tree costs are greater than 8. That's why out of these 4, we select the minimum cost spanning tree is fourth spanning tree. So like that we can construct. But if Prim's and Driscoll's, by using Prim's and Driscoll's algorithms, we can directly construct spanning trees. But if you want to construct spanning trees like this, you must construct 16 spanning trees like this. Out of 16 spanning trees, you must select one optimal spanning tree which contain minimum cost. What is optimal? Optimal means minimum cost spanning tree. Optimal means minimum. So minimum cost spanning tree we must calculate. So that's why we use Prim's algorithm and Driscoll's algorithms for constructing spanning tree. There is a standard or constant approach defined under Prim's and Driscoll's. If you follow Prim's and Driscoll's algorithms, straight away, instead of constructing 16 spanning trees, directly we can construct one spanning tree under Prim's algorithm and one spanning tree under Driscoll's algorithm. We say that those two spanning trees are optimal spanning trees or minimum cost spanning trees. Okay, in next video I will explain Prim's algorithm, and then further videos I will explain Kruskal's algorithm. Once again, I will show you. This is a spanning tree and the spanning tree definition and example of spanning trees. And these are the properties of spanning tree. These are properties of spanning tree. Here I explained the number of spanning trees possible from the complete graph and number of edges which are required to construct spanning tree. And here I defined what is minimum cost spanning tree. And I have given or mentioned the algorithms which are required to construct the minimum spanning tree or minimum cost spanning tree. And I took one example with the four nodes, and I constructed four example spanning trees. And out of these four, I have shown which is minimum. Okay. So this is about introduction to minimum spanning tree or minimum cost spanning tree. In the next video, I will explain. I will explain what is how we can construct spanning trees in Prim's algorithm and Kruskal's algorithm.